name is Native Falson, and today I will be presenting a paper titled A Multi-Cloud-Based, Privacy-Preserving Data Publishing Scheme for the Internet of Things from the ACSAC conference of 2016. This paper was thought to be the first work to utilize a multi-cloud structure to prevent the disclosure of attributes and access policies. Since then, similar works have been published, like in the 2018 IEEE conference from two of the authors in this paper, as well as influencing other academics in their research. In this presentation, we will discuss how secure, downward data transmission in IoT remains a concern, with the authors highlighting the lack of studies produced till then in comparison to upward data transmission. IoT presents innovative solutions to interconnect devices together over the internet, providing an ever more present idea of technology that is accessible from anywhere, making daily tasks more suitable for automation and remote control. Unfortunately, as technology advances, so too do the threats and attack vectors evolve to hinder the advantages of IoT. IoT involves internet access to remote devices, meaning only dedicated setups with encrypted data at rest or in transit can ensure user data is not tampered with or disclosed to unwanted malicious third parties. Given these considerations, the downstream transit path is investigated from IoT service providers to end devices. Conventional and strong message encryption over the internet is typically considered to be in a unicast form, using standard, public, private key pair message encryption to secure the intended messages. Considering the large overhead and the amount of devices managed by a typical IoT service provider, an effective user attribute encryption method for different user device characteristics ought to be considered with the computation of overhead offloaded from the IoT device and into the cloud, which will bring a desirable solution to a real-world scenario. This will also ensure that only the intended recipient receives the intended message. The encryption method considered is called Ciphertext Attribute-Based Encryption, or CPABE for short. This scheme considers identifying a user by his or her set of attributes, similar to role-based access control but more granular. Whilst offloading computation to the cloud, three major concerns are considered when offloading encryption and decryption functions, and they are data privacy, attribute privacy, and access policy privacy. Whilst also ensuring the verification and integrity calculation of messages is still done on each respective IoT device as a desirable design solution. The CPABA schemes considered in this paper are Parallel Cloud Scheme and Chain Cloud Scheme. These two schemes, as we will see later in this presentation, from the experimental results, offer a trade-off between latency and attribute assignment flexibility. Parallel Cloud Scheme is considered to have a rigid attribute assignment, but includes strong privacy encryption and less latency. Chain Cloud Scheme offers flexible customization and more expressive access policies, but adds added latency due to Bloom filter table lookups, which we will see later in this presentation. Parallel Cloud Scheme is also solely based on a series of AND gates to express the policy used. Chain Cloud Scheme requires all attributes to be satisfied and looked up before forwarding to the IoT receiver. Let us look at the architecture and design considered for parallel cloud schemes. As you can see, we have the IoT service providers on one end and the IoT and devices on the other. Each cloud provider has its considered domain, depending on the type of data considered, with the user attributes assigned for each user. An M number of cloud servers is considered to deliver the required user attribute message, where each cloud server operates on the received access structure and ciphertext messages, outsourced originally from the trusted authority, to together deliver the data to different IoT devices. To summarize the steps considered for the scheme, I have detailed them like so, with steps consisting of the setup procedure, where the public key and master key are generated with security parameter lambda, a universal attribute set n, and the considered number of cloud servers m. The key generation procedure for the transformation used for each cloud to perform a partial decryption with the signed user's private key to be able to decrypt the received messages at the endpoint. The encryption procedure for the message M is done using a polynomial calculation from the attribute set defined for the parallel cloud scheme, using the public key in the computation for each attribute. The transformation procedure, which partially decrypts the attribute set to make decryption less computationally costly, is done whilst checking that the intended attribute set is satisfied by what is received. Finally, at the user device, the partially decrypted M ciphertexts are decrypted using the assigned private key and decrypted function with the verification and signature value of the final message confirmed valid. The delegated attributes in the chain cloud scheme are assigned prior to transmission to ensure it satisfies the expressive policy considered for the design. To the IoT receivers, as you can see, no path is the same, as attributes can also be assigned by which cloud is most trustworthy, so to speak. The more cloud servers involved, the more complex the attribute policy assignment. To facilitate the comparison between the parallel and chain cloud scheme, I've highlighted the differences to the parallel cloud scheme in red. This will depict more clearly how, although similar to each other, one varies to the other in the steps considered. The setup procedure, similar to the parallel cloud scheme for this step, produces the public key and master key, but without considering the number of cloud servers m, like in the parallel cloud scheme. A step specific to the chain cloud scheme is the subset delegation of cloud attributes using a considered Bloom filter generation algorithm. This step decides which clouds are to be assigned with which attributes, and if the received attributes are to be processed by the recipient cloud server. The following key generation procedure considers the computed cloud usage specification with the master key, user attribute set, and private key. The encryption procedure follows similar to the parallel cloud scheme, using a polynomial calculation from the attribute set and public key defined. It is important to note that the encryption formula is different to that of the parallel cloud scheme. The transformation procedure will partially decrypt the attribute set to make decryption less computationally costly. Added to this step is how the cloud looks up the attribute in the Bloom filter table and may outsource it to another cloud, possibly introducing false positives as well. Finally, at the decryption end, it is done using the assigned private key with the verification and signature value of the final message confirmed if valid. Both schemes cannot have an unauthorized party decipher the intended message without knowing the correct parameters. Given the attributes are also outsourced to the cloud, it is important to note that trust to the cloud servers is implied with this solution. With the encryption and decryption computation being outsourced, this is a risk implied with solution with each cloud acting on attributes received. This will significantly reduce inference attacks, particularly with chain cloud scheme, where the attributes are delegated to multiple clouds differently. Chain cloud scheme cannot guarantee verification completeness, unfortunately though, which is why false positives may be introduced. Parallel cloud scheme, on the other hand, has this, so long as one cloud is honest. When evaluating the cloud solution, in comparison to original text-based attribute encryption scheme used as a reference, the comparison of delay and latency as the number of cloud used was increased produced to show how latency is more favorable to the parallel cloud scheme, which helps greatly in keeping the solution as real-time as possible. When considering a larger number of attributes in the policy, the original ciphertext attribute-based encryption scheme increased decryption time proportionally, while the schemes introduced with this paper kept decryption time to a constant, regardless of the number of attributes used. To summarize the findings of this paper, these schemes significantly reduce computational overhead at the IoT device, whilst preventing the disclosure of attributes and access policies using the multi-cloud structure, and also allow the IoT devices to confirm integrity of the correctness and completeness of messaging. My personal view of this paper is that it is insightful on how to secure IoT data transmission, with IoT services needing to ensure data security if they are to be kept long term, particularly when we consider the involvement of IoT in more critical infrastructures, such as e-health and smart grid services. This concludes the presentation of this paper, and I'd like to thank you all for listening and wish you all a great day.